How current, wire length and magnetic field affect magnetic force 2. Objective: to investigate the variables that affect the magnitude and direction of the force of the magnetic field on a current-carrying wire. The experiment studies effect of current, effect of wire length, effect of magnetic field simple, meaning we change one variable at a time and observe how the magnetic force changes. 3. Apparatus, basic current balance accessory, Ohaus centogram, balance low voltage, AC/DC power supply, large base and support, rod banana plug cord set, red banana plug cord set, black Data Studio software. 4. Experimental setup. The setup contains support rod and base, current loop, also called conductive foil current direction, magnetic field region, B magnet assembly on yoke balance, ammeter low voltage, AC/D, C power supply. 5. Important note, the current loop should not touch the magnets. 6. Big idea of the experiment case. 1. No current leads to initial mass reading on balance. Case 2. Current on leads to magnetic force appears. Case 3. Balance reading changes arrow. New net mass is measured. Case 4. Net mass arrow. Convert to force using F equals delta mg. Explanation: magnets are placed on a balance. A conducting path is placed between the magnets. When current passes through the conductor, a force is produced. The change in the balance reading is used to find the magnetic force. Main conclusion: balance reading changes because magnetic force acts when current flows. 7. What happens? Power supply provides current. Current flows through the wire. Wire is in the magnetic field. B. Magnetic force is produced. Balance reading changes. Change in mass gives force F equals delta mg8. Theory main. Equation Fm equals ILB sine theta. Definitions: Fm equals magnetic force in newtons, I equals current in the wire in amperes, L equals length of the wire in meters, B equals magnetic field, strength in Tesla, theta equals angle between the field and the wire. Key idea: the magnetic force depends on ILB and theta. Additional note: this infographic focuses only on how force depends on current, I length, L magnetic field, B, the angle is kept constant. 9. Part 1. Force versus current. We keep L and B constant and change the current, I. Steps: use 4 to 6 magnets. Use the same current loop length. Change current from 1 ampere to 5 amperes. Measure change in mass. Find force and plot F versus I10. Part 2. Force versus length. We keep I and B constant and change the length, L. Steps: use 4 to 6 magnets. Change wire length or loop. Use current from 2.0 to 3.0 amperes. Measure change in mass, plot F versus L11. Part 3. Force versus magnetic field. We keep I and L constant and change the magnetic field, B. Steps: change number of magnets. Keep the same current and length. Measure change in mass, plot F versus B12. Data tables. Table 9.1. Force versus current. Record: number of magnets used. Current loop used, mass at I equals 0. Current in amperes, mass in grams. Net mass in grams. Force in newtons. Table 9.2. Force versus length of wire. Record: number of magnets used. Current used, mass at I equals 0. Length in millimeters. Mass in grams. Net mass in grams. Force in newtons. Table 9.3. Force versus magnetic field. Record: current used, length of wire used, mass at I equals 0. Number of magnets. Mass in grams. Net mass in grams. Force in newtons. Note: always record your data carefully and use correct units. 13. Data analysis. Net mass equals mass at I equals 0 minus mass at current force. F equals net mass in kilograms multiplied by G, where G equals 9.81 meters per second squared. Plot the proper graph for each part. Determine the relationship between variables. Find the slope and vertical intercept. Graph. Meaning, slope. M shows how strongly the force changes with x vertical intercept. B gives the value of F when x equals 0.14. Final message graphs tell the story of the magnetic force.